I'm going to talk some about performance tuning on KNL using the tools that we provide in our Parallel Studio. And I'm going to be focusing on some of the new capabilities that are available in our 2017 product releases. First, a few things that we've learned in this workshop, because it's been pretty good. I have had a lot of things. I've learned a lot this time. I hope everybody else has learned something useful. It's been great seeing and hearing what all work has been done and what sort of optimizations you've been working on and seeing the kind of performance you've gotten. But as you've seen, getting that performance is not a simple task. You've got to work for that performance. You've got to refactor your code. You've got to add in libraries. You've got to make sure you're well balanced. There's a whole lot of work that goes into getting that good performance on any system, especially on KNL. Through this, there have been a variety of techniques you've used. I mentioned a few just now, things like refactoring your code, finding bottlenecks, trying to resolve these performance issues so that you can keep getting that performance on both current and on new hardware. As the next generation of Xeon Phi comes around, the work you've done thus far and the work you're going to be doing in the future is going to help you prepare for that, and your code will be that much more prepared for the next architectures. We've also seen that there's a variety of tools available that will help you in this process of gaining that performance, finding those bottlenecks, and trying to make sure that your code keeps on going. And that's what I'm going to be talking about now. We have released our 2017 version of Parallel Studio XE, and it's got some familiar features and a few new ones. Now, my primary talk is going to be about the tools, so I'm going to save that for later. We've got our libraries as usual, and all of these, you've heard some about TBB, you probably know a lot about MKL right now. These are all libraries that you can put into your code and get the performance without having to do as much optimization work yourself, because what we do is before a new product is released, we start working with the hardware teams to optimize our libraries for that new hardware so that when you've got the new hardware and when you've got the new software, those optimizations are already put in there. Similarly with our compilers, we do optimization work ahead of time on those. And that way, you're more prepared for the new architectures when they come out. Now, one thing that's new on here is we have an Intel distribution for Python. How many of you in here use Python? Got a few hands up. Good. I'm going to say a few magic numbers that may get some attention here. What we've done is we've taken the open source Python and we've added some optimizations into it. Those have been pushed back upstream for general use. We've also compiled it with the Intel compiler and linked several of the numeric libraries like NumPy and SciPy with MKL, and that's now bundled as part of Parallel Studio. The magic number that I think is going to get your attention is we compared our Python to standard Python, running the exact same programs. And on some of the benchmarks, we're seeing nearly a 100x improvement in performance just by running under our Python instead of normal Python. That's on both Xeon and on Xeon Phi. So if you use Python, I highly recommend you take a look at this and see if it's something that can help you. And I'm going to link that into the tools because one of the things we've added in VTune that I'm not going to touch on much today is VTune can now analyze your Python code and give you some hotspots and information out of that. So I'm going to go into our tools now and how you want to use those to help you tune your performance on KNL. Now, there are several different methodologies. We tend to recommend a fairly common methodology. Start off with what are you doing at a high level? Take a look at your program. Just general ideas so that you know what areas you want to focus on. And those might be your MPI. You may need to improve some performance there or balance. You may need to work on how you're utilizing your memory. Or it may be related to the CPU And within there, we've got several different areas where we've got, you may need to add more threads. You may need to improve your threading balance. You might need to improve your vectorization, or just how efficiently are you using the CPU. Now, I mentioned this is about tools. We have a tool for every one of these areas. Most of these, if you've ever actually found and seen the icons we have for the tools, they're going to be familiar. We've got VTune Amplifier, we've got Intel Trace Analyzer and Collector, and we've got Intel Advisor. These are all going to help in various areas of your tuning process. One you probably haven't seen before is a companion tool or a companion bundle to Parallel Studio, which is our Intel Performance Snapshots. This is a relatively new thing for us. You might have seen the MPI Performance Snapshot. We've expanded that to include an application performance snapshot and a storage snapshot. I'm not going to talk about storage snapshot today, other than to say it gives you a high-level idea of how well you're utilizing your storage. I will talk about MPI Performance Snapshot and about Application Performance Snapshot. First, I'm going to use the term imbalance a good bit in here. And I've had questions come up before. What do I mean when I say imbalance? Well, when your code is running optimally in any sort of parallel environment whatsoever, you've got your work, you'll have some sort of synchronization, and the work will be basically identical across every execution unit, be that threads, be that vectorization units, be that processes, doesn't matter. But in reality, you're going to have dead time in there. One thread, one rank, something is going to get done before the others will. And that's going to leave that one at some point just sitting there waiting. It may only be a tiny bit, it may not matter, or it may be fairly significant. But that wait time is what I'm referring to when I say imbalance. At any point in here, we've got different kinds of imbalance, but when I use that term, I'm talking about that wasted time that could be used doing something useful. Now, the MPI Performance Snapshot. Have any of you used it prior to the 2017 version? Okay. Oh, we have one. Okay. So you'll notice a few changes in this now. But for everyone else, new tool. What MPI Performance Snapshot is this is intended to be a high-level overview of an MPI program to show you how well balanced you are in your MPI versus your computation, and within your computation, OpenMP versus serial. Now at the moment, we can only detect OpenMP, so if you have threading that's serial, if you have threading that is not OpenMP, it's going to show up as serial. Until we have ways put in to detect that kind of threading, this is what you get. Now within here, this is our new HTML report. So for those who've seen it before, it's changed up. The very first thing you're going to get is we're going to look at that balance of time, and we're going to tell you where do we think you should be doing your optimization efforts next. This particular case, we've got a lot of OpenMP imbalance. You are OpenMP bound, go into VTune. The purpose of MPS is not to solve your performance bottlenecks. It's not even to positively identify your performance bottleneck. Its purpose is to give you an idea, whether you're familiar with your code or whether this is a brand new code, of where you want to be focusing your efforts on. So we're going to give you recommendations of which tool to go to next to get that deeper dive into it. MPS is really easy to use. With the Intel MPI library, you add -MPS to your run command, that's it. If you're using a different MPI, one of the things we've added now is it will work with any MPitch compatible MPI implementation. So Cray MPI, IBM MPI, MPitch, MVAPitch, those will all work. The way you do that now is we provide a wrapper script that you run under your MPI around your job, and that'll preload all of the collection data we need. That imbalance information, we're getting two different sections of imbalance here. We're getting an MPI imbalance and an OpenMP imbalance. The MPI imbalance, We've changed up how we get that, and that now comes from the MPI-T interface. We have in the Intel MPI library implemented MPI-T interface to provide that imbalance information to Performance Snapshot, and we're trying to get other vendors to implement a similar interface so that we can get that imbalance information from other MPIs as well. The OpenMP imbalance, that comes from the Intel OpenMP implementation, and at this point, that's all we've got for now. Now, the next snapshot tool I want to talk about is the Application Performance Snapshot. This can be run on an MPI code, but its intent is you've got an application and you just want to have an idea what is the primary bottleneck on this application. Where should I be looking next? This is going to give you an extremely high-level overview, similar to MPI Performance Snapshot, of how well you're utilizing your CPU, how memory bound are you, and how well are you using your floating point unit. With those three metrics, anything that we deem to either be too low in the case of utilization or too high in the case of memory bound, we're going to give you a red flag. This is very easy to use. I've had several system administrators saying that they're considering using this as a precursor to your job run on the cluster. You run your application under this, give them the output from it, and they will then can even automatically determine what sort of priority should this job get. Is it ready for this cluster? Now, all of the snapshot tools are free. You can go get them at intel.com Performance Snapshot. Get them, try them out. They are, like I said, they're very high level. These won't give you your answers. They will point you in the right direction to start getting your answers without necessarily having to know your code, or if you're working with someone else's code, if you have no idea where to start, this gives you that idea. Now, once you're in more depth, we've got different tools for different areas. I'm going to talk first about our Intel Trace Analyzer and Collector. This is primarily intended for MPI analysis. It can also do more in-depth into your program. There are several different capabilities within there that let you see at different levels. Now, Trace Analyzer and Collector, one thing I'm going to comment on here, we use an event-based approach that is not the CPU events. People, especially when I'm talking about both ITAC and VTune, they use different events. What we're looking at are events within your program. The default ones are going to be MPI calls. We are going to intercept every MPI call in your program and report back to you when did that MPI call happen, what's some of the data that was in that MPI call, and how does that match up to MPI calls in other ranks. Now, the way we let you do this is you've got several steps in your program. The Intel Trace Collector is the component that gives you the data out of your program. We've got different ways you can do that. You can collect at runtime using either -trace or by preloading the library. You don't have to touch your code in any way whatsoever. As long as you're dynamically linked to your MPI, you're good to go. If you're statically linked or you want it in your binary at all times, you can put this in at link time. Or if you want some more depth, you can do this at compile time. With the Intel compiler, we have a tcollect option. What this is going to do is it's actually going to instrument not just the MPI calls, but every function in your code. We're going to tell you when did you enter that function, when did you exit that function, and you can see that information individually for every rank in your job. We also have an API, and that API is going to let you go in and instrument, I want to see what's going on in this particular block of my code. So I'll put an API call in there to mark when I'm in it, when I'm out of it. I'm going to give it a name so that when I go and see it in the results, I can identify what I'm doing there. I can also turn collection on and off. Say, I don't want to analyze my I/O steps. I can turn it off for those. Now, whatever method you use to get your trace, you're going to run it and get trace file or a set of trace files and load those into Trace Analyzer where you can actually see what's going on. Now, Trace Analyzer is organized as a set of views and charts. Each view is a group of charts, and they're all linked to the same time span. So whenever you zoom in on one, we're going to zoom in on all of the associated charts, and they're going to show you different things. We've got charts like the event timeline, that's just what is each rank doing at any given time. We've got quantitative and qualitative analysis that will show you how long calls are taking, histogram of that, or how many of your execution units are in any given function at a specific time. We've got a function profile to show you time spent per function. This can also be broken down to show that time across ranks. So you can see things like, well, rank 2 was spending a lot of time in MPI wait. So maybe I want to see why rank 2 was doing that in specific. We also have message profiles that show you contours of how much data was being sent between ranks, how much time was spent in collectives in each rank. You can get lots of different ways to find where are your MPI-based bottlenecks. Or if you're looking at OpenMP or any other threading, Trace Analyzer and Collector can show you that as well. You can see that in anything you've instrumented. One of the newer features we've added into it is the MPI Performance Assistant. Sometimes these bottlenecks are easy to find, sometimes they're not very obvious. What the Performance Assistant does is it's going to scan your code, or the results from your code, and figure out what are some common MPI problems, how much impact do they have on your code. Here you can see an example of a weighted barrier, which is some of your ranks got to the barrier too soon. That's going to happen naturally a little bit. In this case, the impact is fairly small, but in some cases this might be a large impact. That indicates, okay, I want to go and try to improve my barrier or my load balance so that I'm not hitting that barrier as soon. When you dig in some more, you can see if there are specific ranks impacted more than others by it, and you can drill down to where those calls occurred in your source code so that you can try to resolve what led up to that. Can I rebalance my workload or redo my algorithm so that I get better balance and don't have to sit around and wait? Now, one of the things specific in ITAC about imbalance is we have the idealization capability. What this does is it's going to take your trace, we'll say this is a quick slice of a trace, and we're going to make a new one that is the ideal trace. What would that have looked like if you ran the exact same program, everything worked out identically, but you had a perfect network? You had infinite bandwidth, no latency, all communications, everything dealing with MPI was just instantly done. We're doing non-blocking sends here, so the sends are always going to be 0 duration in that scenario. Get to the send, it's instantly done. The receive, if it happens after that send, it can get done instantly as well. Data's right over there. But if the receive happens before that send, the receive can't get done until that data is there to be transferred. That's how we calculate the MPI imbalance. And in MPS, you can see it as an aggregate over your entire program. Here, you can find that imbalance when you create an ideal trace. You can find that imbalance anywhere in your code, in your run, and see exactly what points are creating that imbalance. Now, our next tool is VTune. A lot of you are probably familiar with it. Quick question, has anyone in here not used VTune? There is no shame in saying it. Okay, so we've got a few people who have not used VTune before. VTune is our performance profiler, and for those who are new, a quick overview. It will capture events on your processor as your program runs to tell you where are your performance bottlenecks, what's holding you back, where do you want to optimize your code. Now, there are a lot of different collections in VTune. There's a lot of information it can give you. I'm going to focus on some of the key areas for Knight's Landing. The first is the high bandwidth memory. VTune has a memory access analysis that's going to let you make sure you're utilizing that high bandwidth memory well. Where do you want to be adding in more allocations to high bandwidth memory? What memory objects are the most significant impact on your performance? The scalability. You want to make sure MPI, OpenMP, any threading or parallelization model you're using, VTune can show you how well balanced that is within a single node. So you've got an OpenMP, if you've got pure OpenMP, well, you can find where are your locks and waits, where are those holding you up, how well balanced were your OpenMP synchronizations, how well balanced is your load within your OpenMP regions. Or maybe you were spending too much time in serial. One of the new features we've added is for an MPI job. Previously, VTune could only run one rank per node, or one instance per node, because once one instance of VTune is accessing the driver, none of the others can access it. We've updated the driver and we've updated VTune such that now, if you have multiple ranks on a node attempting to use the driver, they're all going to combine into one result file, and it's going to differentiate within that result file which rank was doing what. If you're in an MPI job and we can detect that rank number, we're going to show it. If not, you'll still get them as separate instances of that executable, and if you've got a PID mapping for the rank, you can use that to get it. Next is microarchitecture efficiency. This is how well are you utilizing the processor that you're running on? Are your instructions fully utilizing the capabilities you've got, or is something getting stalled somewhere? The general exploration analysis is going to show you a lot of detail of what events are going on. Did you get stalled in cache somewhere? Are your instructions just not coming through fast enough? Are you doing the wrong sorts of thing for maximum performance? And we're going to give you a lot of information on how you can utilize that better. The last one is the vectorization. Now you notice here I say use Intel Advisor. That's because as Advisor has matured, it's a much better tool for vectorization. VTune can still show you how well are you vectorizing right now, but Advisor is much better suited to telling you where you want to go with your vectorization. And I'll be talking about Advisor in a little bit. So VTune's got its own methodology of how do you want to be tuning. Start off with our Hotspots collection and our new HPC Performance Characterization collection. These are going to give you where do you want to be focusing your tuning efforts. You want to make sure that you're doing the right work in the right places in your code. There's no point trying to optimize something that takes 0.1% of your runtime. You're not going to get significant benefit out of that. Once these have identified where your bottlenecks are in general, you'll either go into a general exploration or a memory access analysis, or you can build a custom analysis, but these two are the recommended next steps to show you what is my precise bottleneck and where is this occurring in my code. Then once you've got that, you're going to optimize whatever you're told from there. Memory access is fairly simple comparatively. You're going to find which of your memory objects are using up the most bandwidth and move those into MCDRAM. Depending on which areas you need to work on here, you'll have different approaches. You might need to rebalance your threading, you might need to improve your vectorization with Advisor, or you might need to work on some efficiency steps. I mentioned the HPC Performance Characterization. This looks like Application Performance Snapshot, except unlike APS, you can get into more detail within your code where these problems are occurring. What region of your code is more memory bound? What regions are not using enough floating point data? Not just the overall program. This will let you see, in addition with the hotspots, what are my focus areas? Now the hotspots analysis is easy to explain. This is where are you spending the most time in your code. We're going to give you some indicators in pink, and you'll see these throughout in VTune. Anything that's highlighted pink are areas that we've decided, based on the metrics that you're getting, these are significant impacts to your code that you might want to examine. And these have enough performance impact, they're worth looking at. CPI is a bit of a tricky one, not always the case, but it's the example we have here. Now, once you've gotten an idea of what you're looking at, let's say you need to work on efficiency. We'll run that general exploration analysis, and it's going to give you, it's going to classify what your instructions did as your code ran through. And we're going to put into 4 different buckets based on whether there was an whether there was an instruction allocated, and where that was stalled if it wasn't, or whether or not it was retired. Each of these areas is going to indicate different optimizations that you may need to do. If you're front-end bound, you want to look at the structure of your code. Make sure it's not too branchy. See what you can do to keep the instruction cache going. If you're back-end bound, then you might need to switch over to a memory access analysis, or just make sure that you're staying in cache as much as possible. If you've got a bad speculation, that's going to go back to similar to a front-end bound. Try to make sure your code is well structured so you're not having to pull back those instructions once they're allocated. And if you've got a lot in retiring, that is where you want to be, but you can still do some improvement, or you might still be able to do some improvements there. If, for instance, you've got a lot of divisions in your code, maybe there's a way you can use a multiplication instead of a division so that that's done more efficiently. Or you could be retiring and not using your vectorization very well. If you're not taking advantage of those wide vector units, you can still get better efficiency. Now, how do we show the vectorization usage? Right here in this column is what percentage of my vector width am I using on average on that line of code. Are we looking at lines? No, we're looking at function level. Within that function, what's my average vectorization usage? You can drill down to line level and see on any given line, what is my average vectorization usage? If you get that up to 1, like you can see in a few of those, great. If you're running low, well, these aren't too bad. But if you're running pretty low, you may want to see if you can vectorize it better. If you're running at 0, it may just be something that there is no vectorization there. You may not be able to. Everything can't be vectorized. And one thing I want to point out here is you've got, some of these numbers are grayed out. What that means is that VTune has determined it did not get enough data to give you a good result there. We're still going to tell you what the result is, but we do not believe it to be statistically significant because VTune does a sampling. If you get too much of that in any given run, then VTune's going to tell you, oh, I don't trust this run, you should try again. I'll talk some more about options for that later. Now, the memory access analysis. One of the things with KNL is the high bandwidth memory. You want to make sure that you are utilizing that efficiently so that you are getting the best memory bandwidth you can. Now, you know about the 3 different models of it. One of the things with VTune is we cannot currently differentiate between these 3 modes. The events look the same to VTune. All we can see is you did something in MCDRAM. So, what you will want to do with the memory access analysis is whenever you run it, you're going to want to keep in mind what mode you were in when you ran it. And there's an option in VTune to show the information based on flat mode or based on cache mode. You check the one that's appropriate for whichever you were running, and that's what we're going to show. We'll treat it as a cache hit, or we'll treat it as going out to memory, depending on which you check. And if you're in hybrid, you can check both of them. Now, what you're going to see in the memory access analysis is what memory objects were utilizing bandwidth. What you want to focus on here is which of my data arrays, which of my structures can I put into high bandwidth memory? Which ones need that the most? So the way you want to run this is by running it with MCDRAM in flat mode and nothing allocated. That's your first step, because what that's going to show you are nothing allocated to high bandwidth memory. That's going to show you which of your data structures are hitting that memory bandwidth cap. Those are the ones you want to be moving over first. And if your program fits completely in flat mode, then you can run it completely in flat mode and call it good. But if you've got too much data to fit there, this is our recommended approach to find what data structures are the most vital for that. Now, there are a few other things you want to keep in mind on KNL. KNL is a very parallel system. The VTune finalization process is very serial. So if you try to finalize on KNL, which we do automatically right now, you're going to find that that can be pretty slow. In some cases, okay, it takes about a minute or two. We've had reports of this taking on the order of an hour. Not necessarily what you want to do, especially for a shorter run. So disable finalization on KNL, and then when you move your results over to a Xeon machine, we'll do the finalization when you attempt to open it there. There is, because of the many cores on Xeon Phi, there's a lot of data we collect, because we're collecting events from every single core on that system. So there are two different options you can use to manage that. The first is to change the thresholds we're using by telling VTune about how long do you think this is going to run. Are we running, you can treat these options as I'm running on the order of a few seconds, I'm running on the order of a few minutes, a few hours, or longer. And what we're going to do with that is our statistical sampling has thresholds for when we take data. That's going to change what those thresholds are. As you tell VTune we're going to be running longer, then we'll just bump that threshold up so that we don't get quite as much data. You can also change what the default data limit is. This will let you collect more data. It just means that it's going to take it longer to load, and when you transfer between systems, it'll take longer. Power throttling. KNL will power throttle if needed. VTune can show you this by the CPU frequency ratio. So if you see that this is changing over the course of your run, you can know, okay, my program was impacted by the throttling and I want to either rerun and try to avoid that, or keep that in mind as I'm looking at my performance results, that they may not be as accurate as I was hoping for. Last one is event multiplexing. The PMUs are set up such that we can only collect a certain number of events at a time. The way VTune handles for collections that need more events than what we can do is a multiplexing approach. You're going to have a set of events that we're going to collect on. Once we hit a certain number of those, or a certain threshold of either number of events or time, we're going to move to the next set of events and collect those. Then move to the next set, and we're just going to loop through that as your program runs. Now, if you have a really short run and you don't tell that duration to be very short, you may not get enough data. This goes back to where I was saying your results may not be statistically significant at that point. So what you can do there is, if the target duration type is not sufficient, we have an ability to allow multiple runs. And what that's going to do is, instead of swapping during your run, you're going to swap the events you collect, run it once with these, run your program again with these, run your program again with these, until we've got a full set of data, and then we'll combine all of that. All right. Let's talk a bit about Advisor and some of its new capabilities for KNL. Who in here has not used Advisor? Okay, a few more hands this time around. Advisor is our tool for threading and vectorization prototyping. Now, I'm mostly going to be focusing on vectorization, so all your threading info is going to come right now. With threading, what we do is you run your code under Advisor, and we're going to see what loops in your code could be threaded, how efficiently could they be threaded, and what sort of gains would you get if you threaded it. So in this example here, you can see the estimate on this is you'll scale up to about 26 threads, but then you're not really going to scale up and you're going to start falling off, because we're estimating that the overhead of those extra ranks or extra threads isn't worth it anymore. Now, with vectorization, we're going to do a similar thing for vectorization, but there's more detail in there, so I'll go into that. A few of the new things we've got in 2017, first, are we have increased the vectorization capability to work with AVX-512 more. We've got support for the new KNLs. You can run Advisor natively on KNL, or I'll talk a little later how you can do a vectorization analysis for KNL without being on a KNL system. We have a precise flops calculation. This is not done using hardware counters. We are actually looking at the instructions in your code, and we're looking at the vector masking that's going on, and we're going to calculate from those instructions that are run how many floating point operations occurred in your code. And we're going to use that for some of our analysis later. We've improved our memory access analysis so you can get better information on how your data is laid out in memory for vectorization. We've got a better way to select what loops you want to be looking at for analysis. We've improved the workflow such that now you can do this more easily and more efficiently. And the loop analytics have been improved to give you better answers. So the process for Advisor, you're going to start off, we're going to take the compiler diagnostics out of the Intel compiler, turn on your optimization report, and we can see what was vectorized, what wasn't, and why does the compiler say it wasn't vectorized. You can run your code under Advisor, and we're going to combine the performance data we collect for your entire program with the compiler's optimization reports to give you some guidance on why is something not vectorized, or for what was vectorized, does it appear to be running efficiently? What can you do to improve that? We're also going to get some extra information such as the trip counts and the flops so that you can see which loops are vital for vectorization, which loops aren't really going to be worth it. Now, in addition to these, we have a dependency analysis. The thing with the dependency analysis, the compiler will, by default, play it safe. If you have a loop that it thinks there's a dependency that would make vectorization unsafe, the compiler's not going to vectorize it. You can go in and tell it to, but by default, we're going to keep your code correct before we break anything. What Advisor will do is when you run the dependency analysis, you're going to select what loops you want to run it on, and then Advisor is going to, when you get to those loops, watch the memory accesses as those iterations go. Was there a real dependency, or is the compiler playing it safe incorrectly? So you can use that dependency analysis to determine for sure, am I safe to vectorize or not? The last one is the memory access pattern analysis. What this does is when you go through a loop, when you vectorize, you want your data to be strided or contiguous. That makes it easier for vectorization. You don't have to do a gather or a scatter. It works much more efficiently that way. But you don't necessarily always know how your data is laid out in memory. What we're doing here is we're looking at, for the iterations of that loop, how was the data laid out? Was it all contiguous? Maybe it was non-unit strided. Or if it's irregular memory layouts, we're going to tell you, kind of hard to see here, but we're going to tell you what percentage of those data accesses were in which of those categories and how effective your vectorization will be based on that. Now, some of the things we've added for KNL, I mentioned that we can do the profiling and the precise flops with the mask utilization. I'll talk a little more about the mask utilization and its importance in a little bit. We've updated the advice information that Advisor is going to give you to account for the new instructions in AVX-512 so that the recommendations we give you for is this worth vectorizing or not are more accurate. And we've also added in a gather-scatter profiler. Before, advisor would just say, your memory is not laid out well, you're not going to do efficient. Now, we're going to look at your gathers and scatters and tell you how much impact we estimate that those are going to have. I mentioned before that we can now do advice for AVX-512 without being on an AVX-512 system. The way this works is you're going to compile with those flags so that your code has the instruction path for AVX-512 built into it. You can run it on an AVX or AVX2 system, and we're going to get the data from that run, but advisor will see in the instructions the AVX-512 code path and estimate based on that what sort of gains you could see if you vectorized on AVX-512 instead. And we'll show you in here, here's what you've got actual, and this is what we estimate that you're going to run into. For instance, we've got a gather going on there that's going to slow us down. And what sort of performance gains you could see if you took this code to AVX-512 as it is. Now the mask utilization. I keep bringing this up. Why does this matter? Because if you have these wide vector units, you want to make sure that you're using the entire thing. Otherwise, you're not realizing all of the performance potential you've got there. So what we're doing alongside the flops calculation is we're looking at those vector masks and seeing, okay, in this case, we get 8 floating point operations. Here, we're only getting 5 because we've got 3 of them masked out. That lets us give you better data on how much work you're actually doing and what can you do to try to improve that so that you are utilizing those. Now at this point, a lot of people would do a call to action. I don't like that. I'm doing a challenge instead. What I want you to do is take some of what I've told you today and some of what you've seen from the presentations throughout the week, and I want you to go and modernize your code. I want you to go and put some of these performance libraries in if you've got places to work them. I want you to refactor your codes. I want you to find those performance bottlenecks and improve it. Now, while you're doing this process, document it, because I want to see what are the steps that were taken for this. What did you do? Where did you find a bottleneck? What did you do to improve it? What tools did you use to do it? What techniques are you using to improve your performance? Along with that, capture what performance gains you're getting from doing these optimizations so that there's a record of, well, I swapped my array order from IJK to KJI and I got a 3x performance gain. Let's see that. And then publish those results. The benefit of that, I love the little fortune cookie picture we had up earlier. The benefit of that is that that lets other people benefit from the work and knowledge that you have done. They can use that, they can learn from it, and if they're encountering similar performance problems, they don't necessarily have to go through the entire process again. That work is there for them. You can benefit from others who do this and get that same results or similar results on your codes. Now, I'm not just going to give you a challenge and expect you to walk off with that. We've got some extra resources that are available to help with these. We do a series of webinars every spring and every fall. We recently started our fall webinar series. So if you go here and sign up, you can see what webinars we've got, attend. These are all online webinars. We do them, I would say, about once a week or once every other week on different HPC related topics. So if you see something that might be interesting to you, go ahead, sign up and attend it. Learn something from it. Ask us questions there as well. We've got books in the back. I see there are still some left, so if you don't have one, get one. This is a good book. It's got lots of useful information on the new KNL and how you can optimize your code to take advantage of it. If you don't get one today, or if you want to point someone else at it, you can go to lotsofcores.com and get the book from there. We have several different education resources available. We've got our software developer zone, which we've got discussion forums, we've got knowledge base articles. That's where we keep our archived webinars. We have lots of information there. We have our HPC Developer Conference. That's coming up the weekend before supercomputing. So attend that, go to some of the talks there. We've got a whole series of labs that we're planning as well for that. I can speak that one is a fairly major lab based on KNL performance tuning. So if you can attend that, great, get some extra knowledge there. We have hands-on training for some of our partners to get access to these systems ahead of time, either through the ICMP program or through our Developer Access program. These will let you get onto these systems so that you can start working on them before you necessarily have access to a big cluster of them. Now, regarding the tools, we've got several different options for getting the tools. We've got your standard commercial license with full Premier support on that. That gets you all the updates. That gets you, if you still want to use an older version, we support a few versions back on there. That gets you access to patches, all kinds of things. If you don't need the full support, then for certain groups of people, academic researchers, open source contributors, educators, and students, we've got free versions of the tools available. And these are, some of them are the compilers and libraries only, ranging all the way up to, I believe we even have a free version of the cluster edition for one of these categories. We also have for our performance libraries, we've recently taken our performance libraries, MKL, TBB, IPP, and DAL, and made them completely free. If you want to go download them and use them, software.intel.com/nest, you can get a community license and link it into your code, start using it. There is zero charge for doing this. You want to redistribute the code, totally fine. We also have a set of tuning guides and performance analysis papers. These are guides that are, the older ones are intended for how to use VTune to tune for specific processors. The latest one for KNL, we're adding in some advisor information as well. And we have one for every architecture family, so that whatever you're trying to run on, you have a good methodology of how you can use VTune, how you can use Advisor now, and use that to improve your performance for that specific one. And if you optimize for the more recent ones, a lot of those optimizations are going to carry on to the next ones. You'll actually see as you look through these, a lot of the steps aren't all that different, but there are some specifics for each that are covered. All right, that's everything I have to say about that. So I'd like to thank Argonne for hosting this. This has been a very good event this week. I'd like to thank all of the Intel contributors who have helped put everything together. I'd like to thank the IPCCs for all of their work in educating and supporting the developer community out there. And last, I want to thank all of you for attending. And I've got time if there are questions.
Do you have any questions for our speaker?
Hi, my question is about the overhead when doing analysis with VTune or with the trace analyzer collector. I mean, in some cases, I feel that I have to make the problem size and run very, very short to be able to do it in practically. So what's your advice in general about this?
Which tool are you talking about? Because the overhead for each of them is going to be different.
The trace analyzer collector, for example.
Trace analyzer and collector's overhead is going to be based on how much you're instrumenting. I don't know how bad of an overhead you're seeing, but the absolute worst I have ever seen on a code that was benchmarking thousands of MPI calls and nothing but that was on the order of 40-something%. The average overhead that I see for most programs without a lot of MPI in them is on the order of 5%, I would say. So it can be significant in terms of, yes, you're going to see it, but it really depends on how much you've got instrumented. Now, if you're instrumenting your entire code, you're going to see more overhead. Everything that we instrument, it has to store when did that call happen, what rank made that call, and in the case, well, I should say with anything, there's extra data we can store. With MPI, we store all of the arguments that you sent to that MPI function. If you've got your own instrumented regions, with tcollect, we're not going to store anything other than what's the name of the function that you went into, where is it at in your code. But if you instrument the regions yourself, you can choose with the API what additional data you want to store with that call.
Other questions? A few minutes. So at the time, what we did, we developed a code called Quantum Chemistry Games, and we had an issue. We like to track the memory footprint at runtime. So it's like, what is the actual memory footprint of, like, for example, per MPI rank at runtime? Because you see what happens, each MPI rank actually has different memory requirements and kind of fluctuate. It would be good to know, like, what is kind of bottlenecks we have. So
let me go back then, way back here. Keep going. There we go. With MPI Performance Snapshot, we can track the memory usage, and the one you see on the HTML report is overall for an average of your rank. You're going to see an average, maximum, and minimum. You can go into the command line tool and get more detailed reports on what the memory usage of each was. No, not in MPS you cannot. I don't think, the only tool I can recall off the top of my head that tracks that over time is Inspector. And Inspector is going to map both your program and its memory usage, and Inspector tends to have a fairly high overhead because it's a correctness checking tool. Overhead is not an issue with Inspector so long as it actually runs. But that's going to show you your growth over time if you want to use it.
Thank you very much. Any questions?
Which of these tools also has support for Intel TBB?
What do you mean by support for
So, for
Intel
example,
TBB?
this one here, the performance snapshot, it doesn't the only threading it recognizes is OpenMP.
Correct.
Are there other tools that just if the bottleneck is not enough? For example, one challenge I've had is if I'm using TBB, I can't tell, am I running out of tasks? Are my tasks too small? Or is there some dependency between tasks?
That sounds like it's going to best be handled by VTune. VTune has a locks and waits analysis that will look at any threading synchronization that it recognizes, and TBB is one of the ones it recognizes. That would be my first stop, is go through VTune. As an aside point, you can use Advisor, and in the threading mode, when it gives you estimates of performance gain for threading, it does have models for if I thread using Intel TBB. So you can see what gains what estimated gains you could get from that. And ITAC, the way it recognizes threading other than OpenMP is if there is any MPI call in the threaded region or anything that you have instrumented in the threaded region, be that a function call when you're doing tcollect or an API call in there, then it will recognize, okay, there are threads here, and on everything, instead of just saying P0, P1, P whatever your rank number is, it'll be P0, T0, P0, T1 for which thread it's in. So you can see threading information in ITAC as well. But for your case, I would start with VTune.
So I have a question related to VTune. I had this experience where it seemed like the overhead from the instrumentation was affecting the result that VTune was giving me.
Okay.
So I was increasing the sampling frequency, and VTune started to tell me, oh, all your threads are spending half their time spinning, while with the lower frequency this didn't happen. So I guess the question is like, how would I sort of know the reliability of the result that is coming from VTune? Do you have any advice on that?
Normally, VTune should be able to tell you via, it grays out things that it determines unreliable based on it does not have enough samples for the runtime of what's going on.
I think this was almost an inverse problem, that I was collecting too many samples and the collection was having an impact on.
I don't have specific advice on that other than see me afterwards for my contact, and I will see what we can do about that. But that sounds like something we may need to investigate ourselves.
Okay, thank you.
Any other questions?
It's very nice that you've made these tools available at no cost to the community. Now, I know you have to buy the commercial version to get the Premiere support. What exactly is the developer zone? Is that a place where just anybody with expertise can kind of help each other? Can you say a little bit more about that?
Combination of that. Other than one specific forum on there that is dedicated for licensing type support, the forums on there are intended for discussions on specific topical areas. Some of them are tool-based, some of them are not. And our support engineers are also on those forums. If we see issues, we try to address them. That's part of our support process as well. So you still have access to the support team going onto the forums. It's just a matter of some things we're not allowed to do on the forums. Like if you find a bug in the code in our tools and it needs a patch, we can't provide that patch over the forums. That's a special engineering build that has to come through Premiere support at that point. If you have a code that you want support on, but it's a proprietary code and you don't want to just give it out on the forums, that has to go through Premiere support. So there are advantages to doing Premiere support, but you still get access to our support engineering team and the wider community of developers who go to the forums.
Any last questions?
Can I limit the amount of data based on the rank ID, not on the amount of data that is generated?
What was that?
Can I limit the amount of data output based on rank IDs? Rank IDs.
Rank IDs. I do not believe, I don't think VTune, are you talking about VTune?
Yeah, sure.
Okay, I don't think VTune has the capability to do that at this moment. In the previous edition, before we had the more MPI friendly, I would say yes, you could do that because each one would be its own completely separate entity. But now, since all of the ones on a node are going into one result file, I don't think that's going to work. Basically, now if you still want to only see VTune data for certain ranks, you can still do that. You can do MPI.
Well, yeah, I understand. This is not the problem of looking at the data. It is the problem of getting this data outside of the system.
Mm-hmm.
Any last questions? I think that's all. Well, let's thank again James, our speaker.